Welcome to Animal Behavior. Imagine trying to find your way through a dense, dark forest just by hearing a rushing river. To survive, you need to move directly toward that water source without wandering aimlessly. In biology, this directed movement in response to a stimulus is called a taxis. Today, we are going to master three fascinating types of taxis: Tropotaxis, Klinotaxis, and Menotaxis. By the end of this lesson, you will understand exactly how animals use built-in math and biology to navigate their complex worlds. Let us dive in. To begin our journey, let us look at Tropotaxis. Imagine you are blindfolded and hear music. You instantly know its direction because your brain compares the volume between your left and right ears at the exact same time. In the animal kingdom, this is called tropotaxis. It requires the animal to have paired receptors, like two antennae or two eyes, spaced apart on its body. The nervous system calculates the difference in signal strength simultaneously. The animal then turns until the stimulation is perfectly equal on both sides, achieving sensory balance. Once balanced, it moves in a straight line, directly toward or away from the source. Now that we understand what tropotaxis is, let us look at how it works mathematically. We can define the turning response of the animal based on the difference in stimulus intensity it receives. The formula is R equals K times the difference between SL and SR. Here, R represents the turning response, or the angle the animal turns. The symbol K is a constant sensitivity factor, specific to that animal, which determines how sharply it reacts. SL and SR represent the stimulus intensity received by the left and right receptors. If the left signal is stronger, the difference is positive, and the animal turns left. If they are equal, the difference is 0, and the animal walks straight ahead. Before we move on, let us see this with a concrete example. A beetle is using tropotaxis to find a rotting fruit. Its left antenna detects an odor concentration of 80 units, while its right antenna detects 50 units. The beetle's sensitivity constant is 0.5 degrees per unit. We want to find its turning angle. We start by substituting our values into the tropotaxis formula. Subtracting 50 from 80 gives us a difference of 30 units, meaning the left side has a stronger stimulus. Multiplying this 30 by the constant 0.5 gives us 15. Because the value is positive, the beetle will turn exactly 15 degrees to the left, guiding it directly toward its food. Having calculated the turning angle, let us visualize what this actually looks like. On screen, you can see a diagram of our beetle navigating an odor gradient. Notice the small dots representing the chemical odor molecules. They are much denser on the left side. The left receptor, labeled SL, is immersed in this higher concentration, while the right receptor, SR, is in a lower concentration area. The curved arrow shows the beetle turning towards the left, actively correcting its path. As long as both receptors function properly, the beetle will keep adjusting until the concentration is equal on both sides, allowing it to walk in a smooth, straight path toward the source. This reliance on paired receptors brings us to an important question. What if an animal only has one receptor? This is where Klinotaxis comes in. Imagine trying to find a scent with only one working nostril. You would have to sniff, move your head, and sniff again to compare. Klinotaxis is exactly this, a directed orientation behavior where an animal determines direction by successively comparing intensities over time. The animal moves its single receptor from side to side as it travels forward. The nervous system compares the measurement at time 1 with the measurement at time 2. Because the animal is constantly swinging its head to sample the environment, this creates a distinct, wavy, zigzag pattern of movement. Now that we know how Klinotaxis works conceptually, let us model it mathematically. To understand this successive comparison, we look at the change in stimulus intensity over a small time interval. The formula is delta S equals S at time 2 minus S at time 1. Here, delta S represents the change in the stimulus intensity experienced by the animal. S at time 2 is the intensity measured at the current moment, while S at time 1 is the intensity measured a moment ago during the previous head swing. If delta S is positive, the stimulus is getting stronger. If it is negative, the stimulus is getting weaker, prompting the animal to swing its head the other way. Let us apply this formula to a real biological scenario. A maggot is trying to move away from a bright light source, a behavior known as negative Klinotaxis. It swings its head to the right at time 1 and measures a light intensity of 120 lux. It then swings to the left at time 2 and measures 90 lux. We substitute these values into our successive comparison formula. We subtract the older measurement of 120 from the newer measurement of 90. The result is negative 30 lux. This negative number tells the maggot that swinging to the left decreased the light intensity. Since its goal is to find darkness, it will accept this leftward direction. We have seen animals move directly toward or away from a stimulus. But what if they just need to travel in a straight line across a featureless landscape? This introduces our third concept, Menotaxis, or light compass orientation. If you keep the sun shining exactly on your right shoulder, you will walk in a perfectly straight line. You're not walking toward the sun, you're using it as a fixed reference point. Menotaxis allows an animal to maintain a constant, specific angle relative to a distant stimulus, like the sun or the moon. Because these celestial bodies are so far away, keeping a constant angle to them guarantees that the animal travels in a straight line over vast distances. To understand how insects like ants navigate using the sun, we must look at the geometry of Menotaxis. The mathematics involves maintaining a constant angle between the animal's heading and the line of sight to the stimulus. The equation is theta h equals theta s plus alpha. In this equation, theta h represents the actual absolute compass direction the animal is walking on the ground. Theta s represents the current angle or position of the sun in the sky. Finally, the symbol alpha represents the constant menotactic angle the animal wants to maintain between its body and the sun. If the sun moves across the sky, the animal must adjust its heading by the exact same amount to keep alpha perfectly constant. Let us see how a foraging ant uses this geometric formula to leave its nest. An ant travels to a food source by keeping the sun at a menotactic angle of 60 degrees to its right. The sun is currently located at an absolute compass angle of 100 degrees. We need to calculate the ant's outward heading. We plug in the sun's compass position of 100 degrees and the ant's chosen menotactic angle of 60 degrees into our formula. Adding these together gives us the absolute compass direction. The ant's outward heading is exactly 160 degrees. This establishes the precise outward trajectory of our foraging ant across the featureless terrain. Now that the ant has found food, it faces a critical challenge: calculating the exact reverse angle for its return trip. The ant's outward heading was 160 degrees. To return home, it must turn completely around. In compass terms, reversing direction means adding 180 degrees to its current heading. This makes the required return heading exactly 340 degrees. To find the new menotactic angle, alpha 2, we take this return heading of 340 degrees and subtract the sun's position of 100 degrees. The result is 240 degrees. The ant must now keep the sun at an angle of 240 degrees to safely navigate back to its colony. To fully grasp this incredible biological compass, let us look at a visual representation. On the screen, you see a diagram of an ant navigating across a flat plain. The distant sun emits parallel rays of light, represented by the straight diagonal arrows pointing towards the ground. The dashed line shows the ant's straight path of travel. Notice the angle labeled alpha. This is the specific menotactic angle the ant is maintaining between its heading and the sun's rays. By keeping this angle locked in, the ant can travel in perfectly straight lines over vast distances. It is truly the biological equivalent of a sailor using the stars to navigate the open ocean. We have covered a lot of ground today, so let us summarize the key takeaways. First, we explored Tropotaxis, which uses paired receptors to simultaneously compare stimulus intensity, allowing animals to move directly toward or away from a source in a straight line. Second, we learned about Klinotaxis, where animals with a single receptor successively compare intensities over time, resulting in a distinct zigzag movement pattern. Finally, we examined Menotaxis, a highly advanced light compass orientation that allows animals to maintain a constant angle to a distant stimulus, enabling straight-line navigation across featureless terrains. You now understand the incredible mathematical and biological mechanisms animals use to navigate their world. Great job!